The Oman Natural Disasters Platform is designed to educate communities at risk. In this project, the information related to Oman's natural disasters is integrated in NHMS software. This information includes earthquakes, tsunamis, tropical cyclones, and etc. This information is collected through existing reports, maps, and articles. This system provides the possibility of simulating natural disasters. This system simplifies the identification of high-risk areas. Also, this system can be used for economic and industrial resilience studies of Oman. The Oman Disaster Platform has four main objectives. The first is training managers, rescuers, students, and communities at risk of natural disasters. The second is promoting resilient planning in the strategic planning process of Oman's development. The third is improvement of natural hazards monitoring process in EOC centers. And the fourth is providing scientific information to tourists interested in Oman's natural phenomena. In this video, the demo version of the NHMS software for the ONDP project is shown. In this section, the location of various phenomena is displayed on the online map. For example, the Bima sinkhole, a beautiful geological phenomenon, is on the northeastern coast of Oman. This place is of interest to tourists as a tourist attraction. Part of the information of natural hazards, such as the location of active faults, is implemented as GIS layers in the NHMS software. For example, the Diba fault along with a series of active faults are located in the Mozandam mountains in the northern tip of Oman. This area has a high seismic potential. Also, the Kalhat fault is located in the northeast of Oman. Probably the seismic activity of this fault caused the destruction of the ancient city of Kalhat 500 years ago. Part of the natural disaster information is implemented in the NHMS software in the form of zoned maps. For example, the 7-day rainfall accumulation zonation map for tropical cyclone Shaheen can be viewed on the online map. The average rainfall recorded for this event in Muscat city is 250 to 500 millimeters. Most of Oman's ports are at risk of tsunami. The tsunami of November 28, 1945 is one of the devastating tsunamis in Oman. Based on the simulated models, two main tsunami scenarios can be predicted for Matrah port. The first scenario is simulated based on an earthquake with a magnitude of 6.5 and a large submarine landslide in the northeast of Muscat. The tsunami resulting from this scenario will hit Matrah port within 24 hours and create waves with a height of 6.5 meters. This tsunami causes 201 minutes of inundation in Matrah port. In this situation, Al-Bahri Road will be submerged for approximately 1.7 kilometers. In this online map, the tsunami hazard zoning in Matrah port is shown in red, orange, and yellow colors. For this scenario, maximum inundation at Qarayat port is displayed on the online map. Some areas of Muscat city have the potential of liquefaction. Based on the results of 25 geotechnical boreholes, Hail al-Awamar and al-Mu'ibullah areas have the highest liquefaction potential. The maximum settlement of liquefaction in al-Mu'ibiyah region is about 21 centimeter. This settlement causes extensive damage to buildings. In the NHMS software, the PGA amplification factor is displayed with a grid structure. For example, the city of Muscat is divided into squares measuring 200 to 200 meters. Then the PGA amplification factor information is implemented in these squares. According to this map, Al-Wazarat, Al-Moj, and Sih Al-Maleh region has the highest PGA amplification factor. In NHMS software, earthquake monitoring is done with the aim of damage estimation. In this process, the maximum ground acceleration is calculated using the USGS attenuation model. Then, with the help of fragility curves provided in the HAZ-US project, earthquake damages to lifeline infrastructure and buildings are estimated. This software automatically receives the characteristics of earthquakes from the European Seismological Center every 10 seconds. Then it calculates the earthquake parameters. For example, an earthquake with a magnitude of 6.2 on the Richter scale is simulated in the southwest of Muscat. In the first step, a shake map of this earthquake is drawn. Shake maps shows near real-time maps of ground motion following significant earthquakes. In the second step, the facilities at risk are displayed with pulsating red, orange, and yellow alerts. For this simulation, Aliaj substation is in red alert condition and Barka power plant is in orange alert condition. This system can be used in emergency operations center. This system has educational and operational applications. The educational part of this system is an interactive learning method for natural disasters. In this teaching method, with the help of web-based software, it is possible for people to achieve deep learning. This powerful learning method increases people's awareness of natural disasters around them. The support team of this system is responsible for software performance control, calculation validation, user training, and database development. This team has more than 10 years of experience in natural disasters, such as earthquakes, floods, landslides, etc. Thanks for your attention.